I'm going to hand over to Arman, who's going to present his paper entitled The Secure Framework for Anti-Money Laundering Using Machine Learning and Secret Sharing. So thanks, Arman, whenever you're ready.
Hi there. All right. Thank you for coming to this presentation. So this is some work I did with my supervisors. Many thanks to them, Eckhard, Pfluegel, James Orwell, and myself, Arman, Zand. So a secure framework for anti-money laundering using machine learning and secret sharing. So, yeah. Introduction. So money laundering in the UK is still not accurately been estimated by the UK government. Just a bit of a background. So they can't actually put a figure on how much money laundering there is. It's in the billions, and they can't even put a range on that. And what we're focusing on is the proceeds of crime transferred through public business infrastructure, that is the banks. And what they usually do is they just employ this KYC policy, which stands for a Know Your Customer procedure, which is just to identify and authorize what the clients can do, just to know what the behavior of clients. So this is not just to do with money laundering, but also involved in account security, and in that sense. So the literature review, we focused on the detection of suspicious transactions, definitely more so than detection of entities that may be associated with money laundering. So that is the transaction information, see how we can derive from suspicious and non-suspicious transactions. And obviously, in any sort of field, machine learning is going to be a powerful tool. And in this context, there's been a very extensive systematic review on this, which has been extremely helpful. And there's been many different techniques to do with the positive, true positive rates, the rate at which the algorithm learns, the performance of them. So there's many different ways to compare the techniques. And from that review, there's a lot of them involved in the money laundering, the anti-money laundering context. And apart from that, there's more sort of manual investigative techniques in forensic analysis. So you might have heard of Forensic Toolkit, FTK, that's also used in anti-money laundering by some investigators. Actually, I went to talk to some of them, and they found they've got some idea about how what techniques money launderers use to launder money, right? So one of the talent techniques is sort of like a burst pattern where money gets sent to one account and then it gets split up to multiple accounts, and then those multiple accounts might split up the money again into smaller and smaller chunks. So it's like a tree sort of pattern. So there's those sort of techniques that they look at. So there's been some research challenges, not only for myself, but for the other researchers and papers that I looked at, which was the data availability. Obviously, since we're looking at some quite sensitive information to do with people's money, and that sensitive information related to that, there's some privacy concerns, as in the second point there. And also that everybody there's many different schemes, and a lot of them use their own format. There isn't a sort of standard way of sharing this information. So there's privacy laws and ethical codes to be careful with. So some people might implement something and they're not very careful, or some of them don't know how to go about doing this anti-money laundering scheme. So there's a lot of data involved as well. You know, there's so many transactions being put out in our day-to-day life, and that means that computational performance is also a very important factor. Whether something is, you know, real-time analysis, you know, live analysis, or that you just take some data set and then do some offline analysis. So where did we fit ourselves in the gap? So out of all those issues that we identified, we saw that a collaboration element between the banks would be quite powerful, because if the banks can share more information, you get a better picture of what's going on with where the money is going. So for example, if money is going from a bank A to bank B, bank A is doing some anti-money laundering activity, but bank B isn't part of it, then you don't see what's going on. So a sort of cooperation between them would be quite powerful to get more information and be more accurate. And one way of doing this, being able to get this collaboration, is to use cryptography in a way that gives information some security and privacy. So that's what one of our main focuses is the use of cryptography in our scheme. And consequently, we want to give back results whether some transactions are suspicious or not. So there's an SAR shown. And what SAR is a suspicious activity report, which is a terminology used in the anti-money laundering papers. A suspicious activity report, so a report that investigators can use for suspicious money laundering activity. So we have a main contribution, which is the overall architecture that aims to improve money laundering detection with a security-oriented primary directive. So this main contribution has two interesting aspects to it. There's the application of encrypted data in machine learning to detect money laundering, and the use of secret sharing as a collaborative element in the context of anti-money laundering. So as you can see, we're quite focused on the use of cryptography in this anti-money laundering framework. And that is to say that in the literature review, there hasn't been any big focus on that. Actually, there was one paper that that mentioned the use of cryptography, but it was on the forefront of the paper. It was yeah. So we're trying to use secret sharing to see where that fits in a scenario. We're experimenting with that and see how it goes. So we have a proposed system design of 3 phases. We have phase 1, which is where the banks send encrypted transactions or redacted transactions to an auditor. So that is to say that in this scheme, we have 2 types of entities involved. We have the banks, multiple banks that send transactions to a single auditor, and this auditor will not be able to decrypt the transactions or be able to infer information about any of the information that is sent to it by the banks. So it analyzes these transactions anonymously by using some machine learning algorithm, which we'll go into the steps in a minute. And the auditor, once it finds out something that is suspicious, it will produce an SAR and then split it up into shares, right? So in secret sharing, you have, you can split up into shares for the banks to recover. So that's the collaborative element, that the banks, they send all the information to one entity and that entity gives it back. And if you want to recover this information, you have to collaborate again. And obviously, security is another important issue. So it involves standard public key infrastructure, so PKI, and all of that. So phase one, signaling to the auditor. So each bank converts their respective transaction into a redacted, encrypted format using AES, so advanced encryption standard. And there's different cipher modes for this symmetric algorithm. So symmetric as in you can, with one key, you can encrypt and decrypt. There's CBC, CTR, and the older one, ECB. But in SIV, which stands for Synthetic Initialization Vector, you can reuse a nonce. So a nonce, a number that you use once and throw away, is normally a security issue if you keep reusing it. But in this mode, you can reuse it. And what that allows us to do is to have a more deterministic reversible ciphertext that the auditor is able to pair up different transactions with, although they are encrypted. So pairs of banks involved in the transaction send pairwise signal to the auditor. So the terminology in this diagram is the TY stands for an encrypted transaction from bank B. So it's bank A and B are involved here. The superscript and the subscript is a bank account number, bank 1 to bank 2. So money is being sent from bank 1 to bank 2. And since obviously there's two banks involved, bank A and B, they'll both encrypt the version of the transaction with their own key and all of that. And they'll send both of them together to the auditor. So what this allows the auditor to do is to create a relationship between these transactions, although they are encrypted, although the auditor doesn't know what information there is there, or what it relates to, is that it can still pair them up. And that once information is given back, they can be decrypted by the original encryptors, so that the banks that, right, with their own keys, their own private keys. So the auditor is able to arrange this information in a directed acyclic graph of transactions, and it uses a binary classification algorithm to determine relevant transactions. So a binary classification algorithm, binary as in 0, 1, suspicious or not suspicious, right? So it's going to have a look at what it's given, and then once it finds something suspicious, it will derive a suspicious activity report, an SAR, from the results. So yeah, in the SAR feedback, so the suspicious activity report feedback is split up by the auditor. And what we mean by split up is in secret sharing, a good example of actually in secret sharing is to think of it like how some pirates, for example, pirates, they have hoarded their plunder, they've got a treasure, and they've got these pirate captains. They don't necessarily trust each other, So when they make the map, with the X marks the spot, they split up that treasure map into n pieces, right? N pieces. And then once they have k, which is less than or equal to n, when they have k of those pieces, they can recover the information. So a good way of looking at how Schmidt does this is in this matrix format. So there's a Van der Mon matrix, which is inverted. When you multiply that by the shares, you can recover the coefficients and the original information. And obviously, if you want to create the shares in the first place, then all you have to do is place the Van der Mon matrix on the right-hand side of the coefficients, but not inverted. So that's a very easy way to show how secret sharing is happening. And we use this to get the banks to cooperate in order to recover this suspicious activity report. So we're experimenting on this scenario as a collaborative element. So we did a preliminary evaluation, we did a prototype implementation in Python using all the different phases. That is, we used a fast tree, specifically a fast tree binary classification algorithm. Again, just to determine the output labels suspicious or not suspicious. And this was fed through synthetic data. So we simulated some banks sending transactions to an auditor, multiple banks sending transactions labeled suspicious or not suspicious, which had a nominal data throughput, and it was a real-time transaction analysis. So that is, it's able to, the banks are able to send a lot of information altogether to an auditor. It's going to go through and organize these transactions in a directed acyclic graph and determine the suspiciousness. And once it's done that, it gives back the results. And it's doing all of that in real time. So conclusion, it's promising anti-money laundering framework, which focuses on the security, privacy and collaboration elements. So specifically the collaboration element is very powerful, so that you get more information, you can have a clearer view of what is going on. All of that is still happening because we employ some security and privacy through cryptography. And the downside of that is if a bank is not participating, a transaction goes off to another bank in another country that may not participate or have the same directives as another bank, then you might lose track of the big picture. So that is one important aspect. So further work involves more extensive development of the prototype and evaluation. That is, more information can be derived from an encrypted transaction. You already have the time of the transaction, where you could see it as a tree of transactions. There's a number of children there. There's properties that can be derived from that, and that can be useful to improve the machine learning algorithm. There's also a possibility to be involved with distributed ledger architectures, like cryptocurrencies. Some, with public ledgers, they can have the same framework applied to them, which could be also very interesting. And what the banks use at the moment actually is the existing third parties. So it might be interesting to also involve the cloud services in there. So that's all I have to show you. Thank you very much for listening.
Thank you very much, Arman. That was great,
Yeah.
very interesting. I'll put it out to the audience then. If anyone has a question, they can pop it into the Q&A, and we will present them onto Arman then. I might just ask, so you kind of highlighted there the next steps for developing the framework. Is that something you plan to continue with yourself?
Yeah, actually, I've got a more robust prototype implementation in a different language in C# actually.
Okay.
I originally did it in Python. There's quite some powerful machine learning algorithms in ML.NET, which I'll try out, and also, as I said, the banks use at the moment they're not obviously using a scheme anything similar to this, but they use cloud services to share information between banks after they get some authorization, right? So it might be important to also involve that more next time around.
Yeah, cool. Yeah. Well, I wish you all the best with the next steps.
Yeah.
And you'll be busy, no doubt. I think we might have one question coming up here. Okay. So Mohammed asks, well, he said, thanks for your presentation. And he says, so for your machine learning model, did you train it using a public data set or did you simulate it?
Yeah, that's a good question because admittedly I used the synthetic data, right? So I couldn't get a hold of some real transaction information. So I just had to work on some synthetic data.
I assume in this context it would be quite hard to get real data, right?
Yeah, I mean it's synthetic data, so yeah, it's not going to definitely be as interesting as using a real data set.
Yeah. And then he has a follow-up there. So he says, how will you assess your data and try to compare it with real-world data?
Well, the thing about this paper is that we did a preliminary evaluation, right? So we haven't done a lot on comparing the data, rather that we focused on how the phases will work from one to the next. So that what we focused a lot on is actually the security and cryptography, the cryptography aspect on it, and machine learning is another one of those things that you can sort of swap in and out, and the data there. Well, if you take all the machine learning papers that have been involved in this literature review, then you can sort of apply them in this context as well. You can sort of layer this on top of this scheme. So to put real world data on it is possible, but that's going to be there's going to be further work since we just did a preliminary evaluation with synthetic data.
Of course. So we have time for one more question here from Leo. So he asks, how do you handle class imbalance? Were there any specific techniques you used?
No, not really. So again, the machine learning aspect and the data throughput, that is the synthetic data, it hasn't been a sort of it hasn't been that what's it called, deeply investigated because we just did a preliminary evaluation, right? So
Sure.
we did focus on trying to get all the phases working together and see that it can actually be promising to go on like that. So this is going to be yeah, this is going to be relevant still for some further work.
Yeah, so you're only at the beginning of a long journey, I guess.
Yeah, so yeah, it might not be honestly. Yeah, these questions are definitely difficult to answer because I use the synthetic data.
Of course.
Yeah.
Okay. Listen, that was great. Thank you so much for your presentation.